Product demo is already over. In the conference room, the model answered correctly. The interface looked effortless. The executive team saw the future they had been promised. Then the deployment meeting starts. The answer is not no. It is worse than no. Data center needs more power. The racks will run hotter than the old cooling plan can handle. The network path has to be hardened before agents touch live systems. Compliance wants approval gates before anything autonomous can move data, modify files, or trigger a workflow. None of that appeared on the demo screen. That is where the AI story changes. For the last few years, most people have watched artificial intelligence through the interface, the chatbot window, the image generator, the benchmark chart, the demo that makes a difficult task look instant. That layer matters. It is what people see first. But it is not enough to explain what happens next. Behind every clean interface is a system under pressure. The model needs compute. Compute needs data centers. Data centers need power, cooling, networks, procurement, permits, security controls, and operators who can keep the stack stable when it leaves the lab. And when AI stops only answering questions and starts acting inside real organizations, agent that can update a file, move data, approve a transaction, or trigger a workflow is not just producing an output. It is touching operations. That means permissions, audit logs, governance gates, compliance review, human approvals, and clear limits on what the system is allowed to do. So the next phase of AI will not be decided only by who has the most impressive model. It will be decided by who can deploy intelligence safely, reliably, and at scale across physical infrastructure, institutional rules, and human responsibility. That is the infrastructure turn. AI is becoming a system, not a product. And systems do not scale because they look good in a demo. They scale when the layers underneath can carry the pressure. If you want to understand where AI goes next, follow what happens after the demo ends. Welcome to Quantum Convergence AI. You can access a powerful AI service in minutes. Open a browser, type a request, and get an answer back. What nobody sees in that first response is the chain underneath it: the power contract, the substation, the transmission line, the data center floor, the cooling system, and the people trying to keep all of it synchronized. Every time someone interacts with artificial intelligence, the model does not just process code. It processes electricity. Large language model may not feel power hungry when it is sitting inside a browser. But the moment an organization runs that system at real scale with specialized chips working in parallel, data moving between racks, and nodes synchronized across a facility, energy stops being background context. It becomes part of the deployment plan. The International Energy Agency reported that data centers accounted for roughly 1.5% of global electricity consumption in 2024, 415 terawatt-hours. Its projection data center power demand will nearly triple by 2030, reaching approximately 945 terawatt-hours. Those figures matter because they are not just about total consumption. They describe concentrated demand. AI systems do not need power in the abstract. They need large amounts of power delivered to specific sites, on specific timelines, through grids that were not built around this rate of compute growth. That is where the bottleneck begins. High-demand regions. Power capacity can lag behind AI-driven load growth. New generation needs transmission. Transmission needs permits. Permits take time. The energy delay slows the compute build-out, and the compute delay slows the deployment that looked so fast in the demo. Watershed moment for this dynamic arrived in the Belfer Center's February 2026 report on AI and the U.S. electric grid. Researchers documented that individual AI data centers can now exceed 1 gigawatt hour demand, each one comparable to a small city, while investments cluster into regional hubs that strain local transmission infrastructure far beyond its original design capacity. Grid interconnection adds another delay. Energy infrastructure planners document multi-year queues just to connect major generation or large load projects to existing transmission lines. During that wait, A company can have the model, the software team, and the business case, but still lack a clear date when electrons reach the site. There is also a geographic mismatch most people miss. AI demand does not spread evenly across the map. It wants sites where fiber exists, where cooling resources are available, where zoning can be secured, and where substations can accept large capacity additions. That makes interconnection harder. You cannot simply build a data center next to any source of cheap energy. The constraints are geographic as well as technical. The practical reality is already visible. Grid limits shape where compute capacity can land. Some projects wait on power delivery. Others negotiate dedicated energy contracts instead of relying on connection timelines they cannot control. This is present tense deployment friction. Every AI interface you touch has already passed through a transformer that could have been undersized, a transmission line that could have been delayed, and a permitting process that someone had to navigate. The model's intelligence is real, but intelligence still needs energy to arrive on the grid. And that timeline does not speed up because the demo was impressive. Power reaches the site. Grid constraints are negotiated or worked around. The transformer hums. Now you face the layer most people watching AI from outside never see: what a data center becomes when it is built to run intelligence at scale. An older idea of a data center was a warehouse with rows of servers, machines drawing a few hundred watts, humming quietly, cooled by large HVAC systems and ceilings. You walked in and the environment felt almost mundane: fluorescent lights, carpet tiles, server racks that looked like filing cabinets stacked 10 feet tall. AI data centers are diverging from that template. The machines inside no longer behave the same way. NVIDIA's H100 GPU can draw up to 700 watts per chip, according to manufacturer specifications cited in the CIR paper 001 source spine. A standard AI server with 8 of those GPUs represents thousands of watts of GPU draw before CPU, memory, networking, and facility overhead enter the equation. Now multiply that across racks built for dense AI workloads. The problem is not just electricity. It is heat. That heat begins to break assumptions built into decades of conventional data center cooling. Foresight has documented that AI workloads push rack power density towards 60 kilowatts or more per rack. That is several times what many traditional air-cooled facilities were designed to handle. The ceiling for air cooling is not just an engineering preference. It is a physics constraint. Air has limited heat capacity. Fans can move more air, but they cannot make air carry heat away as effectively as liquid when dense GPU arrays are running hard. That is why liquid cooling moved from future concept to present-day deployment architecture. Liquid systems move heat transfer fluid through cold plates near the chips, or through immersion systems where components sit in dielectric fluid. These approaches handle thermal loads that air cooling struggles to address at high density. But that shift changes the build-out chain. You cannot simply order more servers and assume the building will absorb them. Dense AI systems require specialized plumbing, leak detection, fluid management, power distribution, and operators who understand thermal transfer in production. A rack that looks like computing hardware from the outside becomes part of an industrial heat management system on the inside. Chip procurement adds another timeline. NVIDIA remains a dominant supplier of high-performance AI accelerators, and major cloud providers. Enterprise buyers and independent operators compete for allocation on overlapping schedules. Multiple facilities need similar hardware at the same time. Delivery windows can stretch across planning cycles. The physical hardware is ready only when fabrication, packaging, allocation, shipping, facility power, and cooling are ready together. The build-out timeline compounds everything above. Industry infrastructure reporting commonly places new greenfield data center development on multi-year construction and commissioning schedules. Facility can exist before the right servers arrive. The servers can arrive before the final power path is ready. The power can be present before the cooling architecture is fully tested. This is what the demo hides. Software can move quickly once the system exists. Physical capacity does not move at software speed. Companies are not just competing on model capability or inference quality. They are competing on how fast their physical plants become operational power, racks, wiring, cooling loops, procurement schedules, construction labor, and interconnection timelines all arriving in the right order. The most sophisticated AI system in the world can only do what the physical layer beneath it allows. And that physical layer operates on construction timelines that do not compress just because intelligence has accelerated past them. Power is at the site. Chips are on the floor. Cooling loops are running. Now a company deploys an AI system and asks it to do something no benchmark chart captures act inside the organization. This is where many AI deployments encounter their heaviest resistance. Not from technical failure, but from operational reality. A model that answers questions lives in a predictable box. You ask, it replies, a person decides what to do next. Human remains in the loop. The risk surface stays contained. Put that same system into agents that can modify files, move data between databases, approve routine transactions, trigger workflow chains, or change infrastructure configurations, and the problem changes. It is no longer only a question of answer quality. It is a question of consequence. The mechanics show up through permissions. Imagine an enterprise IT agent asked to diagnose outages and resolve routine incidents. To be useful, it might need read access to configuration databases, permission to write to monitoring systems, access to service management tools, and the ability to recommend or initiate changes. Each permission creates another surface that must be logged, restricted, reviewed, and audited. Microsoft's Azure AI Foundry Agent Factory blueprint points toward this same challenge. Enterprises need layered security and safety processes to build trust in autonomous agents before those agents touch production systems. The existence of that governance layer shows what deployment teams have learned. When AI stops producing text and starts interacting with infrastructure, many prior compliance assumptions have to be revisited. CSA's cloud security work on autonomous access patterns treats persistent permissions in production environments as requiring continuous monitoring, because an agent cannot be managed exactly like a human employee when it behaves unexpectedly. Research on AI orchestration complexity points in the same direction. Each additional capability layer, reading, writing, approving, triggering, adapting, increases the number of failure paths that controls must cover. Compliance teams add another constraint. In regulated industries, healthcare, finance, government contracting, every deployment must survive review processes built for accountability. Compliance officer reviewing an AI agent's permissions needs proof that the system can be shut down, traced, and held accountable at each action layer. The more autonomous the system becomes, the more the organization has to prove where the limits are. Human approval gates become both necessary and expensive. Gates keep risk bounded, but they can also slow autonomous systems toward human decision speed. That tension is built into the architecture. The more freedom an agent has, the more governance it needs, and that governance burden can make it less automatic. Most deployments still negotiate this trade-off rather than solving it once and for all. Governance also appears outside the company. Data centers require local approvals, utility coordination, environmental review, and public trust. Communities affected by large compute facilities can slow or challenge projects when power demand, water use, land use, or local infrastructure pressure becomes visible. Governance layer is not only inside the enterprise. It also sits in city councils, utility commissions, planning boards, and public comment periods. This is the final layer of the infrastructure turn. Die intelligence arrived, power delivered, physical capacity exists, but deployment still runs through organizational memory, institutional caution, human accountability, and local governance. The demo showed a model answering a question. The system underneath has to answer a harder one. Who is allowed to let it act? Under what limits? And who is responsible when it does? If intelligence were only about algorithms, the race would belong entirely to whoever could write the best code. But the bottleneck is not only written on a screen. It flows through transformers. It waits in fabrication queues. It runs through cooling loops. It stops at approval gates built for machines that now act. That mismatch between accelerating capability and physical reality is why quantum convergence AI exists. We follow intelligence infrastructure, the grid connections, cooling cycles, governance frameworks, procurement contracts, and operational limits, because those layers tell us what artificial intelligence can actually become. Benchmarks tell us what a model can do under test. Infrastructure tells us what society can deploy, govern, trust, and sustain. Look at how civilizations have always competed. They built physical systems to carry their core resources. Roads carried trade. Railways carried industry. Energy and telecommunications carried the information age. The next major infrastructure layer is not just a product you download. It is the environment intelligence operates inside, from the server rack to the compliance review board. If societies mistake intelligence for software alone, they will underbuild the systems required to deploy it, govern it, and trust it. Companies mistake a demo for a deployment. They will discover the missing layers only when the meeting starts. That is the convergence point we are tracking. Not just what AI can do today, but the physical and institutional systems that determine what it becomes tomorrow. Follow what happens after the demo ends.